Hi, my name is Hemang Chawla. I am pleased to present our work on monocular vision-based crowdsourced 3D traffic sign positioning with unknown camera intrinsics and distortion coefficients. This work was done along with Mati Jukola, Elahe Arani, and Behram Zonos. Autonomous driving and advanced driver assistance systems utilize 3D semantic maps of road landmarks such as lane boundaries, stop lines, traffic signs and lights, and so on, describing their geometry. These maps are utilized for accurate planning and safe decision making during the drive. However, creating such maps require dedicated collection vehicles with sensors such as LiDAR, stereo cameras, inertial measurement unit, wheel odometers, and so on. Therefore, regularly updating the map to reflect short-term changes due to road maintenance or long-term changes with urban planning is a highly costly endeavor. Crowdsourced mapping can provide an alternative solution to this challenge. By collecting crowdsourced data from vehicles such as taxis that drive around the city multiple times over the week, we can map the 3D positions of semantic road objects. In this work, we focus on the 3D positioning of traffic signs given their importance in safe driving. Such a setup can easily use the global positioning system and a monocular camera for updating the map. Our goal is to estimate the absolute and relative positions of traffic signs in the geodetic and camera frame coordinates respectively. However, this requires calibrating the camera. Previous works, such as Welzel et al. And Dabir et al., assume access to the camera setup. In such a scenario, the camera parameters can be determined using the checkerboard pattern-based calibration. It is also assumed that this perfect calibration does not change over time, which may not always be the case for low-cost setups. Some works even assume that the ground truth size and height of the different traffic signs are known beforehand. Therefore, in this work, we introduce a system for crowdsourced traffic sign positioning from unknown cameras without presuming access to the camera parameters. Here is an overview of our crowdsourced mapping framework. The input to the system is a set of n images and a corresponding set of GPS coordinates. Given the images and the GPS coordinates, we then perform camera self-calibration to extract the camera intrinsics, namely focal lengths, principal point, and the distortion coefficients. These parameters are used to undistort the images and compute the new camera parameters corresponding to the rectified images. Here is an overview of the self-calibration procedure. First, the GPS information is used to identify the portions of the image sequence where the vehicle is making a turn. The turns are necessary for calibration as pure translation is a degenerate scenario due to scene depth and distortion conflation. We utilize the Ramer-Douglas-Baker algorithm to decimate the original GPS trajectory to identify these turns. Here is an example of a turn detected in the Kitty Raw dataset. Thereafter, we reconstruct each turn using CallMap to estimate and optimize the camera parameters within an iterative structure from motion framework. The estimated parameters remove the distortions present within the image, allowing for triangulation-based accurate traffic sign positioning. Before we can triangulate the traffic signs, we need the 2D positions of the traffic signs observed in the images as well as the corresponding camera poses. Given the rectified images, we perform traffic sign detection and associate them across the frames. We use a detector such as SSD plus PaleyNet to detect the traffic signs present in the image sequence. Thereafter, using a Euclidean distance-based tracker, we identify which detections belong to the same object in the scene. The images are then used to perform ego motion estimation, which is scaled and aligned with the GPS coordinates to output the camera poses. We make use of orb slam based ego motion estimation to get the camera trajectory. This trajectory is unscaled and unaligned with the real world. To scale and align the trajectory, we first convert the geodetic GPS coordinates to the local coordinates through Mercator projection. Thereafter, we use the Umeyama's algorithm to scale and align the estimated trajectory with the GPS trajectory by minimizing the mean squared error between them. Finally, using the sign coordinates in the images, the scaled and aligned camera poses, and the camera intrinsics, we triangulate and optimize the traffic sign positions. The sign positions are initialized using the midpoint algorithm, followed by nonlinear bundle adjustment for refinement. The estimated camera intrinsics corresponding to the cameras of different vehicles traversing different locations, the estimated trajectories of the vehicles, and the estimated traffic sign positions are all stored within the mapping database. To evaluate our proposed system of crowdsourced 3D traffic sign positioning with unknown cameras, we first study the sensitivity of the proposed system to the calibration accuracy. Thereafter, we note the calibration performance and show how this will lead to good accuracy of 3D positioning. All our experiments are performed on the traffic signs found in the Kitty Raw dataset. We observe that the traffic sign positioning is more sensitive to underestimating the focal lengths. However, this is not the case for the principal point, for which the 3D positioning is equally sensitive to under or overestimating it. The 3D positioning performance also improves with loop closure. More number of loops, as in sequence 5, leads to higher improvement when compared with the improvement corresponding to sequence 7, which contains only a single loop. The error in estimation of principal point or distortion coefficients compensates for the impact of error in focal lengths on the traffic sign positioning. This is because the nonlinear bundle adjustment during reconstruction of turns for calibration also minimizes the reprojection error similar to the triangulation of the signs. We also note that the 3D traffic sign positioning is more sensitive to the errors in estimation of principal point and focal lengths than the distortion coefficients. With this, we evaluate the camera self-calibration. The errors in estimation of the sensitive parameters, namely focal length and principal point, is nearly 1%. The error in estimation of the distortion coefficients is larger. Our system is able to calibrate the camera using all the sequences except sequence 4, which does not contain any turns. Our system achieves an average relative accuracy of 24.1 centimeter and average absolute accuracy of 1.295 meters on 8 out of 10 Kitty sequences. Traffic signs in sequence 1 are not triangulated due to tracking failure in orb slam. Similarly, the traffic signs in sequence 4 are not triangulated because of the lack of camera calibration on the account of no turns. This measure corresponds to relative accuracy of 26 centimeters on all frames where the signs are observed and an absolute accuracy of 1.38 meters for all the signs. Thus, with our system, we are able to demonstrate accurate single-journey crowdsourced 3D traffic sign positioning from unknown cameras. Here is an example of some of the mapped traffic signs in Germany using our approach. Thank you.